Hello, everyone. Welcome to this seminar. It's my pleasure to introduce Harry van der Weijde. He's here for giving the seminar and also teaching for a standard course. So we took the advantage of having Harry also for the seminar. I was thinking of for a long time to have Harry here for a seminar, so it's fantastic that's finally happening. So a bit of a formal introduction to Harry. So Harry is head of research and market development at Open Energy Transition, a global nonprofit dedicated to advancing open source tools and data for energy system planning and operation. Harry holds a PhD in economics. He held academic positions at the University of Edinburgh. Actually, when I was visiting Edinburgh, Harry, you were a lecturer or senior lecturer there. He has also, he also held academic positions at Cambridge and in Erlangen, Nuremberg. And he has worked a lot on as a policy advisor for the Dutch government at TNO. Harry's work focuses on energy system modeling, market design, and at the interface between research and institutional decision making. So Harry, the stage is yours. Thanks for coming here. And we're looking forward to your.
Thank you. And it's nice to finally be here. I was thinking yesterday night, I was actually supposed to come here just before COVID hit. Remember this? We had this all plan. So I was going to DTU, and then I was going to Trondheim as well, and I had a whole itinerary planned. And then one day before, everything was cancelled, which is probably better than one day after. Otherwise, I would have been stuck here. But yeah, somehow never made it to DTU in 15 years of energy modeling OR work. So it's great to be here. And thanks for coming here. So yeah, Chilla has already introduced me, so I don't really need to do that again. I asked ChatGPT what title I should give my presentation, and this is what it came up with, as something a little bit provocative maybe. And I'll give you the conclusion right now, so that when the rest is boring, you can just go to sleep. And that is, I think here at DTU and at other universities, people are doing great work on energy modeling and on mathematical methods and technologies in the full range. And normally I would say that's great. That will eventually, you'll publish papers about this, people in industry will pick it up, some people will start trying it, and maybe, eventually it will find its way into the real world. Problem is we have a deadline. If we're serious about our climate targets, then depending on which country you're studying, by 2040 or 2050, we should be carbon neutral, economy-wide. Now, in agriculture and other sectors, there will be methane emissions, which you cannot really capture. So electricity will probably have to be carbon negative by that time, and actually before that time, because electrification enables other sectors to decarbonize. So we have about 10, 15 years to make the electricity system carbon neutral. So this kind of traditional world where we do academic research and we solve problems that are just interesting, publish about them, and then eventually they will be adopted. I'm not sure we can manage that in 15 years. So we need to make sure that the research that you're doing and that all other people in other universities are doing is as aligned as possible with what we need in the real world, and to make that transition easier so that we can do it quicker. And that's basically the conclusion of my whole talk. But I'll give you an introduction to what we're doing at Open Energy Transition, some of the projects we're working on, and some conclusions that I found. So I spent, as Stella was saying, I spent about 10 years in academia, and then a couple of years in more in energy policy, and now in, I suppose, the private sector. I don't know. And so I work a lot with system operators and utilities, and I'll give you some conclusions about the things that I learned along the way. So this I probably don't have to tell you this, but I want to start with this anyway. Yeah, I don't want to stand in front of the screen. That's why maybe I should tilt it even more so I can stand here. Is that good? Right. Yeah. So you all know this, right? We need energy planning to support decision making. And in fact, we probably need more and more of it as energy systems are becoming more complex, more interconnected. You know the story, right? We need them for operations, we need them for regulation, we need them to be innovative, but we especially also need energy models to know how to invest. And going back to what I previously said is we need to accelerate this push from academia to the real world For me, that means facilitating investment. So how can you make sure that the things that you're doing will actually help someone invest in something, or maybe change their behavior, but at least change something in the real world? And of course, we have a whole bunch of tools for this that have been used for decades. Is that like who in this room works on power systems simulation, power systems modeling? So most of you. So you know tools like Plexos, BSCC, Power Factory, and they're great tools. I have no problem with them whatsoever. And they've kind of served the whole industry well for the past decade, and they've definitely had an enormous impact. They've enabled us to do things that otherwise we wouldn't have been able to do. So they fill most of the needs. There is usually good support, so it's easy for organizations to adopt them. They have a phone number they can call if it stops working. They're widely known. There are quite a lot of people with, for instance, Plexel skills. So what's the problem? The problem is customization is usually limited. So if I am a system operator suddenly wanting to do something that I wasn't doing before and I need new functionality, I need to create a ticket with Energy Exemplar if I'm using Plexels. And they have to, depending on my contract, they have to respond to me within 4 weeks. And then if they need to create new functionality, it might take a year. If I'm a system operator in the middle of a crucial planning process, and system operators are always in the middle of a crucial planning process, you know, that even that 4 weeks can be a big problem. So customization is lacking. Also collaboration is more difficult because these licenses for this software, if you're not in a university, are extremely expensive. Typical European system operator pays €500,000 for a single Plexos license, single user license. They typically need more than one user. And that's electricity only. If you want to also model gas, then you pay an additional €500,000. So that's, you know, for an integrated system operator, like in the UK, that means 1 million per user. That's for a system operator doable. Still a lot of money for them. So especially in Southern and Eastern Europe, they often opt, for instance, not to buy the gas package and to just accept that they cannot do integrated modeling of electricity and gas. But it's especially difficult for NGOs, researchers outside universities, environmental organizations to interrogate these models, maybe to check the assumptions. So collaboration is difficult even on use, but then there's no collaboration on development. There's a single team that develops the model. And if you come up with nice mathematical methods, they will not end up in there. Well, I've talked about affordability, I think another important point is transparency. So these tools have been developed over many decades. They're probably very good, but there's many things I can't check about them. And when that's the case, we end up in a situation, we were talking about this earlier, the UK nodal zoning pricing discussion. There was the government commissioned a study from AFRY to use their bid3 model to quantify the benefits of moving to a new market model, essentially. AFRY said it doesn't make sense. A couple of other organizations commissioned FTI to do exactly the same study, but with their model. That said, it does make sense. And the entire discussion after that was, which model do you believe? No, my model is better than yours. And that's not the discussion we should be having. That's not an adult discussion. The discussion we should be having is which assumptions did you make? And how does that affect the results? And which of these assumptions is more believable? The model is really not that interesting. It's just a kind of calculation tool. But if you don't know what's in it, you cannot have this adult discussion. Finally, and this is coming up now more and more, digital sovereignty basically doesn't exist if you use these proprietary models. So Energy Exemplar, for instance, but actually most of them are American vendors owned by American venture capitalists. We've seen, for instance, recently in the Netherlands that the International Criminal Court lost its access to its email services provided by Microsoft because Donald Trump said you can no longer collaborate with the ICJ. This was always a kind of hypothetical situation that these large American firms will stop providing services to organizations in Europe that they don't like. It's no longer hypothetical, it happens. So if you are running kind of mission critical processes, do you really want to be reliant on a server somewhere in the US or a vendor that can withdraw your license at any time? Or do we want, in Europe, for instance, do we want a European solution? Do we want something that's completely locally owned? So that's why I think And that's also why at Open Energy Transition, we're advocating for open source solutions. Because that addresses all these things. And we're trying to do whatever we can to make these open source solutions mainstream and to make sure that everyone can use them. And there's a picture that my CEO often puts up. You know, if everyone makes their own products, then we have 3 separate products, and it takes a lot of time to develop all of them. But we can also collab with open source. We can collaborate on building blocks. We can collaborate on data pipelines, on solution algorithms, or whatever you think is in are the basic building blocks of energy models. And then there can still be proprietary firms that build something on top of it, an additional service that maybe not everyone needs, or that people are willing to pay for to get better service. Then I skip this. So, and we've seen this in other sectors as well. If you look at your phones and laptops, then basically everything is built on a couple of common building blocks that are open source, that everybody collaborates on, but then each brand builds their own service on top of it to differentiate themselves. And I think this is the sort of system we should be having for energy modeling, that there are common building blocks. At Open Energy Transition, we'll build a fully open source stack. But maybe there are other companies. With A3 in the UK, we actually have an active discussion. They agree with this model. For them, they say the data sets that they have are their strategic value add, but we can still collaborate on solution algorithms, converters from one data format to another, data standards and whatever. And actually this open source technology powers often has a reputation, I think, for being of lower quality, because it's free, but it powers pretty much everything in our lives. If you use the internet, you use open source software. Definitely, if you use Firefox or Chrome or whatever, you use the browser as an open source basis. Most of the security layers on the internet are based on open source software. So we're already there. It's already part of our lives. And for these, nuclear submarines use open source software. And obviously not only open source software, but they use some open source software. So we're already in a situation where this is used for the most critical things we use in our daily life. So it's really not an argument to say that this is kind of amateurs doing something in the room. So as I said, what we want to do at OET, ambitiously, is to make open source based energy planning a standard by 2028. It means we don't have a lot of time, about 3 years. And the way we're trying to do that is, first of all, do very visible institutional pilots. I'll show a couple of them later. So we try to work with organizations like NSOE, like large system operators in different continents, and really help them replace their proprietary tools with open source tools to also show to the rest of the sector how this works, and building credibility. We also do some tool development ourselves because, well, many of the open source tools that are available are very good, but also many of them are still good, but developed by academics who used it for a research project and maybe didn't think that at some later point someone else would want to use the same tool. They're probably also not software engineers, so the code maybe doesn't quite look professional enough. It's the thing about open source, anyone can see your code. So if you're trying to actually ask a system operator, for instance, to adopt it, then they can see whether it looks professional. So that means, like, does it have unit tests? Does it have automatic functional documentation? And all the software engineering stuff. We also work on data and data infrastructure, because you can have the best model, but if the data isn't there, then it's useless. And especially, so in Europe, for instance, data provision is quite good. You can run models with publicly available databases, like the Pan European Energy Model Database. But for instance, in Africa, there's hardly any data on grids and where they are. So there we also spend some effort, and I'll show this a little bit later on, to try and complete these data sets so that everyone has access, not just to the models, but also to the data that they need to run them. And finally, we also help people adopt it. So we do training, events, and we provide support, so service level agreements as well, so that these organizations, again, have someone to call when it stops working, like they currently have for their proprietary solutions. And let's see. So this is, in other words, what we do. So we're really young, founded in 2023 by one of my PhD students, Max, and a PhD student from TU Berlin, Martha. In those 2.5, so we're now 2.5 years, I think. In these 2.5 years, we've grown to 51 people. We're 100% remote, So everyone works from home in more than 20 countries, which is a challenge. But actually, one thing I've discovered is this, working from home when everybody works from home is much easier than working from home when some people are in the office, because then you miss stuff. If everyone's remote, then everyone has to adopt good communication practices. And yeah, this is, in other words, what we do is the software development, data work, services and training. We also do some consulting work because some organizations don't have in-house modeling capacity yet. So then, and they still have questions, for instance, what's the value of iron air storage in the German energy system? Was a recent study that we did. And then we do the study for them, but then we still give them the model afterwards so that they can let someone else build on it for the next study, or maybe they want to try it themselves or whatever. And we work with system operators a lot because those are the kind of big projects where we can have a lot of visibility. So we work with NSOE, the organization of system operators, to try and make an open source workflow for the 10-year network development planning process, which they currently use Plexus for. And because we're a non-profit, so we're about 50% philanthropically funded, mostly from Breakthrough Energy, Google, Gratitude Climate Foundation, Sequoia Climate Foundation. And in terms of what tools we use, so in principle, we're tool agnostic. We don't want to just push one particular open source model. There's a whole range of open source models out there, and there isn't a single best one, I think. We do a lot of work on Pipeside, Python for Power Systems Analysis, because it's the most widely used tool by far for medium to long-term planning problems. So there's about 10 to 20,000 downloads every month. And about 100 developers from, I would say, at least 50, 60 institutions. So that's the kind of community that you need to also prove that it's sustainable, that it's not just a PhD student somewhere in an office making this tool and maintaining it, and then when they graduate, then there's nothing. But for short-term power flow modeling, Possible is a much better tool. Pipeside is really kind of static power flow, medium to high voltage levels. Possible is great for also even down to dynamic power flow. Panel power also good for shorter term problems. GenX is a Pipeside-like model, but coded in Julia, which is popular in the US. And we also have some developers for osmosis and time, so the whole systems models that are not just energy specific, but include the whole industry. And energy models are one thing, but you need a lot of other things to make them run. You need data, you need reproducible workflows, you need GIS functionality, you need IT implementation. So we also have software engineers who work on these kinds of tools. But Pipeside is at the moment, we have a lot of Pipeside developers also, because we basically hired all PhD students and postdocs from the TU Berlin. So we have all Pipeside developers and maintainers, all core maintainers outside the TU Berlin work for us. So it's it enables us to develop that faster than other packages, because we're not dependent on someone to accept our PRs in the repos. But the other tools are sometimes better choices. So now I'll just go into, I think I have 6 conclusions based on the work that we've been doing. And so my first conclusion is this is working. There are more and more organizations that are adopting open source tools, especially in Europe. In Europe, I think this ball is really rolling. In the US, it's maybe starting to move. In Africa, Southeast Asia, Latin America, we need to do a little more work, basically. And why can I say that? I can say that because of the projects that we're doing and what we're seeing in these projects. So one of our flagship projects is this open source 10-year network development plan, which is funded by a bunch of philanthropic organizations, because getting any money out of NSOE is really hard, because it's an organization with 40 members and you have to get basically all members to agree to spend money, which is not going to happen. So we took a route around that by asking for money from Bill Gates, basically, and he came through. So we're working on this now. There is this here, the development is actually happening open source as well. So there is if you go to the GitHub for open energy transition, there's an OpenTMYNEP repo with this model, which you can already use now. You can use it now electricity only. We're adding sector coupling is in the progress, and is in progress, should be done by the end of the year. And the goal here is, so NSOE does this 10-year network development plan. They get a lot of data from national TSOs. They process it, and then they generate scenarios. It's a scenario building stage. And then they do cost-benefit analysis of new interconnectors. So those two steps, scenario buildings and CBA, is what they historically use Plexos for. I've already told you about the downsides also that the TSO members are telling us. So we want to make a complete open source workflow so that anyone can replicate also the same NP, but also anyone can run the same model with different assumptions, or run the same model to test their technology and say, and then, for instance, to go to a government or NSOE and say, hey, I'm a storage developer, and I think my technology is actually a lot better than what was in your model. If I put my parameters in your model, then maybe you should build this additional interconnector. And that's the kind of discussions that we want to enable. So this is based on pipes now, because in this case, because it's the most appropriate model, but also because it's widely used, this really needs an active development community. And in terms of technicalities, it's basically, the modeling is fairly simple. It's a unit commitment economic dispatch model and a capacity expansion model. The really hard part is everything around the model. Because NSOE, like some of you are working with TSO, so you probably know this, data pipelines are a mess at most system operators. Typical NSOE data gathering process is, national TSOs sometimes sending CSV files by email to someone else, and then they select one column and manually copy paste it to another document. So when we asked NSOE, can you give us the data for the past time NDP, which was last year, they said, yeah, we don't really know whether we can do that because the people who worked on that are no longer here, and we're not sure. We don't have version control on our scripts, so we don't know which version was finally used. So actually, we spent the past, I would say, 6 months trying to reconstruct what data actually went into that analysis, which is crazy because this is one of the most important energy modeling studies in Europe, and this should all just be, and it's not hard. It's put version control in your scripts, have an automated data pipeline. So we're building this now for them because otherwise we can't do the modeling. But NSOE is very, very supportive, and they have said that if we can prove basically that this gives similar results to what they get from Plexos, they will at least adopt it in parallel to Plexos, so that TSOs that don't have Plexos licenses can still contribute. Of course, we hope that they'll replace Plexos eventually, but this is also politically difficult. No TSO wants to say that they are thinking about moving away from Plexos because Energy Example has threatened that they will then withdraw their license right now. Questionable business practices, but okay. This is a different type of project here. This is a project for NESO, the new UK independent system operator, essentially, an energy system operator. So they no longer own, the UK has split the national grid from NESO. And NESO wanted a market model specifically. So a model where the main output is hourly market prices, or maybe 50-minute market prices, but they're no longer part of the European market, so we don't need to do that just now. And there we really set out saying, okay, we want this open market model, but we don't know which open source model is most appropriate. So we did a very detailed study into a number of models and also Plexos. So we had a database with, I think, more than 100 characteristics of energy models, and these are all kind of similar type of energy models. But it's down to the level of which individual constraints are included by default, or can you include all the way to does it have a GUI, does it have integration with other software, and then in this case we didn't set out to choose PipeSub, but it came out on top. So we are building this now, and the idea is that here the system operator will use this model itself, but also because it's open source, it can share it with, for instance, technology developers. So again, they can then, for instance, test their technology and say, what if we put a battery or a wind turbine or I don't know what here, how does that change the UK market? And let's see, what else do we have? So Transnet is every modeler's worst nightmare project. Transnet is a German, southern German TSO, and they actually were already using PipeSA. But 7 years ago, they had made a hard fork of PipeSA, and then they continued developing on their own fork. And they have quite a large team working on this. So 7 years of development by 3 to 4 people. And in the meantime, the PipeSA main branch became sector coupled, so it switched from electricity only to electricity, gas, CO2, and everything else. And we modularized it and changed a lot of other things. And now Transnet BW came and said, can you make our version compatible again with the main branch? Because we really want to benefit from all this new functionality that was added. So we said sure, and nearly drove one of the Pipeside developers mad, because yeah, you can kind of, if you do some coding, you probably know what this is like. Is you have versions that have diverged for 7 years, and you somehow need to bring them together again. But it worked. So they still have their own private fork. Maybe I have a slide about that later on. They still have their own private fork. It's not public. So they use an open source model, but they use it in-house without publishing it. It's also fine. But they use what we call a soft fork strategy. So they make sure that their fork always stays compatible with the public open source version. And the main way you do that is if you want to do really big changes to your model, you don't do it in your own version, but you do it in the upstream version. That takes a little bit longer because then it has to be reviewed, but the advantage is that they stay compatible. So it's an easy concept, but it works for them. And it also shows that you can use these open source models in a completely separate private in-house setting. And I think maybe finally, or the final flagship project anyway that I want to mention is that we're currently working with ACER, the European Organization of Regulators, to build the software that they are going to use for their new flexibility needs assessment, which they will need to do this year, the first version. And again, this is one of these projects which is about 20, the model is not that complicated, but it's about 20% model development and 80% other stuff. And other stuff in the case of ACER is mostly complying with their very long list of security requirements. So this is also learning. We were also learning by doing this project, because to really put these open source models in these kinds of environments, they need to comply with ISO standards. They need to talk to internal registration systems for user logins and all that stuff. And it's not enough to just have a model. I can't really say what the model does exactly, because Acer doesn't want intermediary projects published. I think they will make the whole thing open source at the end of the project. However, there is also, NSOE also does a similar exercise called the European Research Adequacy Assessment, which of course we take a lot of inspiration from. And what that is basically is, so at the core are two market models, a day ahead unit commitment model, which optimizes your unit commitment using forecast renewables and forecast demand. And then an intraday model where you put the actual data in. And in the era, they also co-optimize reserves in the market. So reserves are kind of approximated. So you have these market models, they run rolling horizon. So 24 hours at a time, and they keep rolling over. And then you create hundreds of copies of these models for different random outage patterns. So you essentially do a Monte Carlo simulation where you randomly take lines. So you have a whole bunch of these operational models, all rolling horizon. So you can already start thinking about how many model evaluations this is going to end up with. And then we have a capacity expansion module, which sits on top of that. Because the market models with this Monte Carlo simulation will enable you to calculate the distribution of revenues for all the assets that are currently in your system, but also potentially new ones. And then adding other revenue streams that are not modeled or that come from other models, you can calculate the profitability of assets, and you take them out if they're not profitable for a period of time, or they exceed a certain hurdle rate, or you put new ones in. And then you iterate with the market models until it converges. And you need maybe 50 iterations to get a reasonable degree of conversion. So you have 8,760 runs for day ahead and for intraday, times, I think, about 200 outage scenarios, times however many iterations you need to converge to your capacity with your capacity module. That's a lot of computation. I think we calculated at one point that it was something like 1 year of computing time to do one single full model run. But then, of course, a lot of this can be parallelized because all the outage patterns can be done separately. And if you send it to a cloud computing service, then you can all do this within a day. So it's still doable. And maybe you're wondering why don't we just use a stochastic capacity planning model? Because then you could do the whole thing in one go. That would be a really big stochastic capacity expansion model. So you need to decompose it anyway and split it into different problems. And essentially, if you ignore the unit commitment, essentially what we're doing is a Gauss-Seidel approximation to a stochastic problem. So we decompose it a different way, and that has the advantage that we can really easily bring in other revenue streams from other models flexibly. And also you kind of see the capacity evolving as you go through your runs. So you see you have more information about what the incentives are.
But we don't know whether we will converge or not.
So if there are no unit commitment decisions, we will. That you can prove. If there are unit commitment decisions, then I guess technically you can't prove it, but in practice,
It converges.
it converges. Yeah. The convergence is quite tricky. If you just kind of update, it takes forever. So you need smart updating rules. And also you can warm start your problem every time with the previous run, and that saves a lot of time. And you need some kind of dampening factor to make sure you're not iterating between two local equilibria, and you need an algorithm that detects whether you're iterating between two equilibria and then chooses something in the middle. So it's not trivial, but implementing, I don't know, Benders or some other decomposition model method on your stochastic capacity expansion model would also not be trivial. So. And Benders would probably not work on a problem this size.
Question about this. So I have been working at the Danish TSO and now doing industrial PhD with them, and I'm specifically in their ancillary service department, which is responsible for their part of their flexibility needs assessment. But it was my understanding that it was supposed to be divided into each TSOs, which would then provide their own modeling, and then ACE would just sort of stick it together in this report.
No, each TSO does their own modeling, and ACE does a European-wide assessment.
Okay.
I'm part of advisory board of this one. This is different than ancillary services. This is more on how the capacity expansion in Europe would look like
Okay.
without ancillary services.
Okay.
So this is the kind of longer duration flexibility. So you look at metrics like energy not served, LOLE, but also how much each technology is contributing to flexibility, and you look at price peaks, and so it's longer term flexibility. And this is the European-wide assessment. The TSOs do their own. But of course, all the data that goes in here still comes mostly from the national TSOs. So data on the networks and on the generation assets and on the reserve requirements all comes from the national TSOs.
Sorry, can I ask what would be the input weather data for doing all of this?
That's the what's it called again? The European Climate Database. Pan-European Climate Database. Yeah. So most of it comes from there, and most of the other data comes from Pan-European Energy Modeling Database. It's basically ACE's own databases. They also have some databases which are not public. They have unit level cost data, which is, they say, very confidential. So we don't have access to all their databases. So I'll show you later how this works. And finally, I want to mention, because data, some of you might be interested in data, we also have a project on grid mapping, because as I said, in many places in the world, there is no public data on where the grids are. So we have a project, again, funded by Breakthrough Energy, to map the world's medium to high voltage grids and to put all that data in OpenStreetMap. OpenStreetMap for Europe, by the way, is already really good. I don't know if you've looked at the energy data in there. It's probably 98% complete. We found lines in there that are not yet in the official system operated data, because this is a community initiative and people are obsessed with this, and they spend their free time looking at satellite images for lines that are not in the data set yet. If that sounds fun, go to mapyourgrid.org. And because we've developed a toolkit to help everyone map it much easier. So for instance, there's a tool, you can bring up a country and it will show you all the substations that are not connected yet. Now, we know there's probably a connection there. So what you do then, you go to satellite images and you see if you can see the shadows of the power towers and then put the lines in. Or you see if you can find other publicly available data that says where lines are.
But what about parameters for the lines then?
If you can find publicly available data with some line parameters, then you can also add them. But everything has to be independently, someone else has to be able to independently verify it. You cannot use data that you have that is not published under an open source license. Which also means you cannot always use system operator data that they publish on their websites, because sometimes they publish data on their websites, but they don't put a license there, and then you cannot use it.
So there are lines in the system without parameters.
Yes.
Okay.
also controversial, but there is this company in the US called Palantir that may be a lot of money because they know how to process data for military application. I was wondering, because I'm complete for external, right? Then I was wondering whether there is some knowledge transfer that you could gather, or whether they really invented something that is really new, or whether, because you were there, right, in the front line for the energy transition, whether we could learn something from them, what they've done.
With these US tech startups, it's often unclear. It's often really difficult to find out what it actually is that they're doing. Google's energy modeling efforts also fall in this bucket. I think they are promising a lot, but we don't actually know what they're doing. It's really difficult to combine these kind of data sets that these companies have, even if they wanted to combine it with these open data sets, because it has to be in the rules of OpenStreetMap are that someone else needs to be able to verify it. And there are cases where system operators, because distribution networks are difficult because you cannot generally see them on satellite images. So there is no, unless someone publishes it with an open source license, there is no data. There are DSOs that have offered to put their data sets in OpenStreetMap, but then that has to be, the community has to vote on that every single time for every single contributor. We're still discussing how to deal with this. Maybe we need to create a sort of parallel to OpenStreetMap where we're a little bit more flexible, and we can add also more electrical parameters, because the same thing, like if we want to add new parameters to this data set that are not in OpenStreetMap, the community has to vote on it, and the community can be difficult. But it's also a great community, because there are, like, if you find a substation, for instance, that is not connected and you really cannot find anything on satellite images, you can flag it, and then people who are local will just drive there and take a picture. And it's amazing that like the whole French network was basically mapped by one guy who spent all his free time looking at satellite images to map the network, and that's why in France it's basically 100% complete. We collaborate with him now on this initiative. So if you want to have a look, if you need a new hobby, look at mapping your grids. And people tell me it's really fun if you find a line that's not in the data set yet and add it. Just move on. So this is the longest conclusion also, so the rest of it will quicker. So the second conclusion is there are probably too many energy models. Why do I know that? So we made this open source energy model tracker. So we trawled GitHub for all energy system models. So power flow, capacity expansion, production cost modeling as the kind of main categories. And we found 208. This is, I think, just showing production. So this 174 is just production cost modeling and capacity expansion. That's a lot. But then if you start looking at, how many contributors are there, how many forks, how many dependents, how many other packages depend on it, and how many downloads, there's a kind of top tier where for capacity expansion and production cost modeling, pipe size is definitely on top with definitely if you look at downloads, but also if you look at contributors and the number of forks and the number of dependents. And there's a couple of others that are used a lot. There's ETM and some other Gen X's here as well in the top. And after that, it drops off pretty quickly. So there are a lot of people creating energy models that are basically not really used by anyone else, which is a shame. Yeah. And okay, so this is filtered for PCM CEM. If you would look at power flow modeling, then Panda Power would be on top, and Possible would be somewhere there. And again, you see the same thing. So there is a kind of handful, maybe up to a dozen open source packages in every category that is really actively developed. But there are also many that sort of stay within one group or within one company. And that are not used very widely. So this is also available at openmodeltracker.org. So if you want to look at these models, we're going to extend this with more functional comparisons. This is just a comparison of usage, but as I said, we did the study already into 100 different ways that models are different, and we are somehow going to add this. Difficulty with that is then we ideally also want to add Plexos as the market leader in commercial software, and we're kind of slightly afraid of their lawyers if we do that.
And could you just elaborate on the score? How do you score?
So basically you as a user can give all these things a weight, and then it will give a score. We don't give a score. So if you find the number of contributors really important, and you can give that a really high weight, and if you think, like myself, I don't care about stars, then you give that 0 weights. So this score is user defined. So yeah, openmodtracker.org. And what we see, because of course we can learn something from open source developments in other areas that are already further advanced. If we look, for instance, at cloud orchestration, then when this kind of started, there were a whole bunch of different companies that had open source software alternatives. And as the market matured, this kind of, some of them dropped off, some of them merged. And where we are now is we are basically left with one package that has, is the kind of de facto standard. So we see that for cloud orchestration, we see that for cloud observability, where again, we started with a lot of tools. After a while, there were 2, and then these 2 merged into a final tool, though ASO still uses Splunk, by the way, but regulators are always a little bit behind other organizations. So in all the kind of successful open source with Linux, we've seen the same thing. You see a whole bunch of tools, and I think that's where we are in energy system modeling world now. We're kind of here. There's a whole bunch of tools, and some are now starting to drift to the top just because they have an ecosystem which is sustainable. And a sustainable ecosystem means there's money. So there are also, it's not just universities, but there are also companies that are using and contributing to these tools. So then it's no longer dependent on funders. The ecosystem sustains itself. So we're kind of here, and it remains to be seen which models will kind of turn out to be. There's some exciting new models being developed in some places. So I'm not saying pipe size is going to be for capacity expansion modeling is going to be the solution, but maybe some models will merge. But I think this is useful to think about also when you are doing your research. Do you need to create new models, or do you want to join a community that already exists? And hopefully with this open tool tracker, it can help find this out, because I think for really, if you want open source energy modeling to be mature, we need to be here somewhere. And we're currently here. So there needs to be some consolidation. Opinion, not a fact. Third conclusion, if you're doing any energy modeling that you think other people might want to use, think like a software engineer, and also think a bit like systems engineer, or hire them. And also hire some security people if you want it to be adopted. This is a lesson that we had to learn kind of the hard way. We had a lot of energy modelers and a few software engineers and no SecOps people, and we've had to hire them. And what that means is, if you want tools to be adopted, it just needs to be professional software. So it absolutely needs to have unit tests, despite the fact that everyone hates coding them. Automatic functional descriptions are really helpful to make sure you always have up-to-date documentation. But there are lots of packages that can help with this. There are also packages that we use, for instance, within Pipestone to do automatic quality control, so that automatically formats your code according to a standard, and it flags it when particular things that you're doing are not the correct way. Making it modular really helps. Pipestone is not super modular. We're trying to implement that. So for instance, in the sector coupled version, you will find constraints relating to different sectors kind of bunched up, which makes it really hard to swap out one sector with a different model. And also document every single thing from the very beginning. If you wait until the end of your project to document, then you're lost. The ASA project at the moment, and this is a model that's based on Pipestone Europe, so that's already pretty well documented. The ASA model documentation at the moment runs at 300 pages. And it's probably going to go to 500. Because every function needs to be described and every assumption needs to be documented. And if you do that throughout, it's not a lot of work. If you do it at the end, then it's bad. And if you look at these 208 models in our tracker, many of them are very badly documented, which means that no one's using them. Also helps if you make it open source from the beginning and not develop your whole thing and then decide to make it open source, because if you start out knowing that other people are going to see this, you do things differently. You document more. You take maybe fewer shortcuts in your coding to make it work. So we've seen with organizations that have models that they now want to make open source that it's a huge barrier because it's made for internal use. It was never designed to be used by others. And if you set out open source, then it's much easier. And also finally follow data standards. You know, we have or are in the process of having, for instance, standards for grid data in Europe with the CGMES. There are not a lot of open source models yet that are compatible with it. So if you want models to be used in industry, then you need to use the data standards also that are used in industry. And that also helps interoperability, because if you do that and other model developers do it, then you can easily link models or interchange data. And that's a big mess at the moment in the energy modeling world. Yeah, what should I say about this? So IT infrastructure requires a lot of thought. This is why you need to think as a systems engineer. So this is an example, a typical example architecture for a regulator TSO project, which is relatively complicated. So you know, you would have, there's usually some private data that even we as the developers don't have access to. So we need to have a separate separate test environment and a separate production environment with SSH authorization in between. So the developers working here cannot access this database. So actually all this stuff in between is not modeling, it's software engineering basically. And even software engineers struggle with designing a platform like this. So we're actually in the process of hiring a systems engineer also to do these kinds of things, because this is, even for software engineers, this is hard. I think I'll leave it there. And I've already talked about the soft fork strategy, so I don't really need to, I'm not going to talk about this, but this is basically, you know, you can have private forks, but do any main developments upstream so that you remain compatible to avoid sending people like us crazy in 7 years when people want to merge things again. If you want to know more about that, I can tell you in a lot of detail. Yeah, don't focus on models alone. As I already said, most of our projects are about 20% modeling and 80% other stuff. I stole this picture from a friend at Gurobi. So, you know, you have your model, in this case PipeSA, but you also then have your model builder. We use LinuxPy a lot, but if you use Pyomo, maybe then you should probably switch, but that's another option. I can give you some figures to show you why you should probably switch, or Gurobi Pi or whatever. So you need to pay attention to what you use here, because especially with models that take a long time in model building, you can really speed things up by choosing a different model builder. Pyomo in particular for large models is really, really inefficient. So if you use Pyomo and you spend a lot of time in model building, I had a chat with a German regulator, and they have some models that can take hours to build and then solve relatively quickly. And I'm not quite sure what they're doing, but and they use Pyomo, so maybe recode your model in LinuxPy or Gurobi Pi, but then you're locked into Gurobi. Then you need a solver. Well, you need an API to the solver, and then you need a solver. And this is one annoying thing about open source energy modeling, is that we don't really have open source solvers that are good enough yet. HIAS is kind of getting there, but for these kind of Acer-like environments where we need to solve millions of model instances within a specified time frame, it's a factor 10 at least slower, and that's not good enough in many environments. So definitely as a community we need to invest also in the solver ecosystem. And to help with that, we've also built a solver benchmark. So this is also available. Do I have it? No, I don't. I can give you I could put the URL on this. It's on here actually, openenergybenchmark.org. So we have a whole bunch of energy modeling problems, from PipeSA, Times, GenX, Sienna, Timoa, and a whole bunch of other models. Small ones, large ones, LPs, MIPS, and we basically benchmark them regularly against all the open source solvers and Gurobi. Why not other commercial solvers? Because Gurobi doesn't allow us to. Gurobi, if you were around in 2018, you know that Gurobi is very hesitant to be benchmarked. There's a whole story around that, but they allowed us to, they give us free licenses to do the benchmarks, but we're only allowed to benchmark them against the open source solutions, just to show what the gap is. And so you can select, you know, what kind of problem you have, whether it's large or small, whether it's an LP or a MIP, and which kind of model, and then you can see how the different solvers perform. And Yeah, if you look at Garobi versus highs, and like if you take all the, well, there's some filters applied here. I'm not sure. This is pretty much all the problems, then it's still a factor 4 to 5 slower. Which can in an ASA-like project is the difference between waiting 1 day or 5 days. So that's kind of tricky, and highs times out sometimes as well. So it doesn't actually solve all the benchmarks. You can submit problems to this benchmark if you use energy models. Doesn't matter what they are. You don't have to submit the model. You just submit the MCP file, which makes it very hard to reconstruct the model. So it's not so confidentiality is not such an issue, and then we'll include it in the benchmark next time, because we need to have as large as possible set of models so that no solver developer can game the system by tailoring the solver to the specific sets in the benchmark. Okay, so I have like 3 minutes. So, and I have 2 more conclusions. So, main challenges, I think, with open energy models and might and not adopted more, user friendliness, interoperability. You need to pretty much be a Python developer to use PipeSA. We're trying to work on that. There are other organizations making user interfaces, but they're not there yet. So that's a problem. Plexos has a GUI. It's a bad GUI, but it's a GUI. Python doesn't, well, actually has one commercial one now, developed by a UK firm called Bayesian Energy, and no open source one as far as I know. The other one is interoperability. It's really hard. All these models make different data assumptions. Even just converting, hourly demand data between different models is tricky, because what does hourly mean? Is it like in the middle of that time period, at the beginning, the end, the average? You have to know quite a lot about the models to make them interoperable, and that as a community we should definitely work more on. Yeah, pay attention to your governance models. Maybe not so interesting, but no, I'm going to skip this. And as I said, key for open source longevity is a well-funded ecosystem, which means money. So industry adoption is really key. So look at what's needed to get these packages adopted by industry so that they also start contributing, and then this philanthropic support can, even if that disappears, software will still be around. And there's still lots to do. And I think what's to do, especially, is, so I already mentioned user interface interoperability, bring advanced methods to energy system models. That takes far too long. All the modeling that we're doing is very simple. You're developing really cool new methods. Why are they not in there in a way that they can be used? There's hardly, the pipes has just got 2-stage stochastic functionality. That's like 15 years. That's technology from 15 years ago. So that's how long it took. And if you have, other things, they should go in there, and they should go in there quickly. Most models still miss some features, but that we're catching up with Plexos relatively quickly, so that's not a problem. User friendliness I've mentioned. Decreasing runtimes for simple models is actually quite important. These ASER models are not very complicated, so they tend not to be the kind of models that OR people work on. You want to improve the performance of super complicated MIPS, not simple LPs, but actually these simple LPs, we run millions of them. So if you make a 1% change there, it has a big impact. So maybe don't always look at the hardest problem, but how you can make the easiest problem quicker. Data standards would make life a lot easier. Interoperability with proprietary software helps adoption. We're currently building a Plexos PipeSA converter. For instance, that's tricky because Plexos has about 1 million ways to define things, but at least it will convert 95% of your model. Open data sets that are really enterprise grade. So like, I think the OpenStreetMap data, where it's very clearly documented. There's very good metadata. It's very clearly documented what data is allowed to be in there. That's also really helps. But I think my main message again is let's decrease the time that it takes for the stuff that you do to end up in these models that seem promising from an ecosystem perspective, and make sure that we have these technologies in there. Thank you very much. And if I can ever do anything for you, then send me a message.
Yeah, also I think Harry will be at DQ until Thursday?
Until Thursday.
So feel free to reach out to Harry directly. But we have 5 minutes for a couple of questions, maybe. Any questions?
Sorry, really quick. I guess the TYNDP project that you're doing is based on PipeScience,
Yes,
which already includes TYNDP. So what's the new things that,
data.
how it is running?
Data. So the pipes Europe also takes its data from ER5, but not from the Pan-European Climate Database. And now it comes from the Pan-European Climate Database. And the capacities in pipes of Europe don't come from PMMDB. So we're exchanging these with PMMDB. The network, so we use the NSOE's network reduction. Also, so we've created shape files for the NSOE network. So it's basically swapping out all the data from the from pipes of Europe to the official data sets. Some cases it's the same data, but then
Very short question. One is, what is the typical thing that companies ask you that is still not in pipes in Europe or in pipes? What is what they are missing? And then maybe a follow-up. There are many people in the room who are PhD or postdocs who are using pipes EU and have contributed to pipes EU. What would you recommend to them on how to maximize their impact?
Okay, so first question, what's the most asked for user interface? In terms of technical stuff, cascading hydro. Maybe not so much for pipes of Europe, more for pipes of Earth, but even in pipes of Europe, that should just be in there, and someone just take a couple of weeks to implement it. In pipe sites, yeah. Well, anyway, we really need cascading hydro also to be able to model in the global south, and also implement future climate scenarios instead of just past data, because especially countries with lots of hydro, looking at the past is just not good enough. So those are just a couple of things that I can think of.
And for PhDs and postdocs, they can increase their impact.
So actively contribute and get in touch with us or with the people at TU Berlin or the other maintainers, and be part of this. You can become a maintainer of Pipes of Europe or of PipeSA. The way to do that usually is to start contributing some stuff and then eventually take a bigger role. And yeah, anything that you develop outside PipeSA Europe or outside one of the used system models, maybe look at, in the end, how can you contribute it to whatever model fits best. So if you have a nice stochastic dynamic, or I don't know what methods, then try from the outset to think about, maybe in the end I'm going to contribute this to one of the bigger models.
To expand, you said that in parts of the world, lots of work has to be done. What type of work? Could you expand a bit on what you meant by that?
So, so in the global south, it's the same. So in Europe, at least system operators and regulators are starting to use this utility. So that will, I think, even on its own, will go further. Especially in Africa, there are many system operators who don't even have planning tools available, or they have a Plexos license, which is currently funded by USAID, and probably, no, this is actually true. And then probably in 1 or 2 years, it's expiring, and USAID has withdrawn its funding, and then they have nothing. So we need to get these tools in the hands of the planners there. Problem is that usually the level of technical knowledge is lower. So there, especially user interfaces are really key. We're starting a project next month with a system operator in Zambia, and Zesco to do exactly that. They have no long-term planning tool. They use, I think, Times or something like, or Leap for their long-term planning, but it has no geographical resolution. So they cannot actually, they can do some kind of energy system stuff, but not plan individual lines. So they have nothing. So we're going to build a PipeSA-based system for them with a user interface so that they can use it and then see what happens. Problem is there's no money there, so you always need to get the money from third parties. But
what would the third party in this case?
In this case, Quadrature Climate Foundation.
One last question, if there is any. Waldemar, the last one.
Yeah, you mentioned something about Julia and the US and issues with that, and then I don't recall what the package is called. It's called power modeling, something.
Gen X?
That was another one also, but yeah,
Yeah,
yeah, you mentioned that those were issues with Julia, but what is yeah, is it specifically because they implemented Julia there's issues with using those, or what were your?
No, I don't think it's issues. I mean, I like Julia. The problem is there are fewer Julia developers than Python developers, so they're also more expensive if you look at average salary rates. And for this kind of modeling, it doesn't really matter because most of the time is spent in the solver. So okay, Julia is maybe a little bit more efficient. everything leading up to it, that saves you 5 seconds, but it doesn't matter. And if you don't have to pay your developer 10 to 20% more, that's the difference.
Sure.
So therefore, we kind of like Pipestyle, but we have some people who do Julia stuff.
So Julia turns out to be fast to solve your linear programming models. If you have to solve a million stuff, would you switch to
Yeah, but Julia doesn't solve it.
Yeah,
So
so
that's
Julia-
no, but that's the thing. It's the solver that solves it. So if you have a problem where everything until you pass your MCP file to the solver takes is a lot faster than Julia, then you should be looking at using it.
Yeah, last question, Anna.
Very quick, like, would you then, like, also regard open source, like, would you recommend going towards like using Hives instead of Gurobi Pi, or what would you recommend? Because right now we're all using Gurobi Pi, but it seems to me that, you know, maybe in the future it might be better to go to Hives, or like, what would you recommend?
Someone needs to spend a lot of money on Hives and alternatives to make it better. I think there's a new version of Hives coming up that is, we are going to see a big performance increase, but of course Gurobi is also not static. I don't know. I think so. Of course, Gurobi is not open source, but I'm kind of relaxed about that because once you pass a problem to the solver, there are very few additional assumptions to be made. So it doesn't really matter if it's black box so much as it is for the model, right? It would be ideal, but of course, Gurobi is expensive. But we like Gurobi. We collaborate with them a lot, so they also support this open source ecosystem. So they're not one of the bad guys in they're not Plexels. But I think we especially need solver developers to focus on open source software, and solver developers are a special breed of people. You don't just find them on the streets. So that's not something that we in this room probably can do a lot about. That needs serious funding.
Good. Thank you so much, Harry, for this wonderful talk.